of Unit 5, Lesson 3, so rational function asymptotes. So just before we even look at anything, how many of you guys remember where do asymptotes come from in rational functions? What causes asymptotes? No, but that's a good mathematical vocab guess there. Can't divide by zero. Exactly. Okay, so when you have a rational function, first of all, rational means fractional, right? That's what rational is, something put in fraction form. And when we have rational functions, we have our variables on top and bottom. When we have variables on the bottom, there's variables that can make the bottom 0 now. That's a problem. Those are called asymptotes. Now, I'm giving you the quick summary here while you're still alive and awake, okay? There's two types of asymptotes slash issues with when 0's on the bottom. There's the one where the number is 0 and can't be canceled, it can't be simplified. That's just straight up a vertical asymptote. The graph will not touch that line. It'll break and it'll have its asymptote there. There's another one where you do, remember when you guys did Math 20 where you canceled off a term that got rid of your non-permissible, but you still called it a non-permissible, right? So you canceled it, but we said, no, you can't say it's gone. It's gone for your simplifying, but it's not gone in terms of your non-permissible, because what that creates is a hole. And so your graph continues on and has an open dot at that spot and then goes through. So it's kind of a little bit different. You have one that looks like this, and we're going to talk about these, like I said, I'm jumping the gun a bit. But you have the vertical asymptote where you don't cancel. It's like these guys. You have the this and this. And then you have a hole, which is like that. Like I just have simply a hole. The graph just continues on. Can't be there, but I can be everything else. Okay? So those are two types of things we're going to talk about over the next 2 days. Okay? Just a quick summary. All right. So rational functions, we just talked about this, simply is your functions in terms of fraction form with you usually have variables on top and bottom, or one or the other. So what I was talking about here, discontinuities. Since rational functions are expressed as fractions, the denominator cannot equal 0. That's the main issue that we're talking about within these two sections. If the denominator of a rational function can be made equal to 0 for a particular value of the independent variable, then this is called a non-permissible. Okay, that's what we talked about already from Math 20. Note that not all rational functions have non-permissibles. So just because you have a rational function, don't automatically think there's an asymptote. That's not true. Because look, this is an example of this one does not have any problems. Nothing makes this 0. Right? X squared plus 1? Because I need x squared to be negative 1. Is that possible? It is not. Okay, so there's just making sure you understand that it's not always that way. Okay. If a rational function has a non-permissible value, then the graph of the rational function will not be continuous at a curve. So if it does have a non-permissible, it won't be continuous. It'll have a break, a hole, it'll have some type of issue because of the non-permissible. So that causes a point of discontinuity if it's not continuous. Okay? All right, so there must be some continuity. Okay, so these are the types of discontinuity. Infinite, which is what I told you is the asymptote you just can't touch. Okay? Point of discontinuity is like there's a hole in the graph. That's where there's just something that was canceled, okay, but it's just a hole of just that specific spot. Okay? We're going to examine the behavior of the graphs of rational functions that have infinite. Okay? And the next lesson we're going to do the ones that have the point. Okay? So today we're focusing on the just straight up vertical asymptote lines. Okay? All right. So graphing a rational function using a table of values. So consider the rational function 1 over x minus 1. Since division by 0 is undefined, what's the non-permissible of 1 over x minus 1? Simply what? 1, right? We put a 1 in that simple 1 over x minus 1, that's your non-permissible. Complete the table of values. So when you put in -5, you get -1/6. You put in -2, you get -1/3. Then you get -1/2. You get -1. You get not defined. You get 1, 1/2, 1/3, 1/4. Okay, this is going to come up quite a bit in calculus too, if you plan on taking that. But to investigate the behavior of a rational function near the non-permissible values, we include values of the independent variable close to the non-permissible. So we're going to get really close to it. See how we're doing 0.5, 0.9, 0.99, and we're seeing what's happening. And that just tells you what's happening where that graph's going towards asymptote, because we know it can't be the asymptote, right? So we know we can't get anything here, right? And so we're looking what's happening towards it in both directions. It's called like in behavior. We're just trying to see what our graph is doing at that point. Okay? So if you plug those points in, you're going to get -2, you get -10, and you get -100. So you can see that this thing is, what's it doing? It's diving. It's diving down. Right? So you see it's just falling off. Then the other way, coming in, it's going to be 2, 10, and then 100. And this one's taking off. Okay? And so then you can go ahead and graph this. So if you have the understanding that the asymptote's at 1, so we know it's going right here. That's the asymptote. And we have a few of these points we can plot, like 0, -1. And we have 2, 1. Those are my invariant points, Lauren. 2, 1, 0, -1. Okay? And so here is what your graph's going to be doing. So at -0.5, it's -2. And then you see it just keeps going down like this, so it gives you that idea that it's going like this. At 1.01, or 1.5, it's 2. And then it's 10, which we keep 10's way up here. And so you see it's going like this. And so that's your graph for that rational function. Okay, any questions on that? Is there anything that I just assumed that maybe you didn't know? Okay, so one thing to know is that the horizontal is an asymptote. Okay, the reason it's an asymptote, it's going to be an asymptote for all rational function where the bottom's growing more than the top. Let me say that again. And I'm not sure, I need to look. In calc, we do ones where the top's growing faster, but for these, what I'm saying is, see how the bottom is 1 over x minus 1? This is staying a 1, right? It's not moving. This can grow. So that we say the bottom's growing faster than the top. So if your bottom numbers are growing faster than the top, notice that as you plug in x's, you're going to get a really big number on the bottom. And as your number gets bigger on the bottom, what happens to the value? 1 over 100, 1 over 1,000, 1 over 1,000,000. It's really close to 0, but never gets there, right? And so 0 is never going to be touched, okay? So that's the horizontal asymptote, okay? Because the fraction will never be 0. It'll get really close to it, it'll get really tiny, but not there. Okay, all right, let's answer the questions they have, okay? Sorry, I think these are interesting, so I kind of get off track a little bit. Okay, so you can verify with your graphing calculator. Make sure you're using the calculator in these. Sometimes they do a weird little break look. So you want to adjust your window or just know that break right there. They're trying to show you the asymptote. Sometimes they look like this on the TI-83s. It'll go like this, like that, and it'll have like a little, I don't know, little break. It looks weird there. So you kind of identify that as an asymptote. So just keep in mind if yours looks like that, that's what it's trying to do. But anyways, describe what happens to the value of the function as x gets more positive. So as x gets more positive, okay, as it goes to infinity, what does y approach? Y goes to, we just said this, it goes to 0. So as your x gets bigger, your y gets smaller but approaches 0 but doesn't get 0. That's what we just said. Describe what happens when it goes to negative infinity. Same thing. Y gets to 0. Okay. But it's just negative. It's on the bottom of it. So like this one, for example, okay, if I did x is 1,000, well, what is it? It's 1 minus, it's x minus 1, yeah. So it would be 1 over 999. And if I did x equals negative 1,000, it'd be 1 over negative 1,001. Those numbers are both super tiny, okay, approaching 0. Okay, from the options below, in the curly bracket, circle the correct alternative in each of the statements below. So as x gets closer and closer to the non-permissible, the value of 1 from the left approaches what? So what it's saying is, so if I'm coming from the left side of the graph that we drew, does that graph come up at the asymptote or dive down at the asymptote? It dives down, right? That picture you just drew? Okay, look right here. Dives down. Coming from the left, it dives down. So dive down is negative infinity. It's going down. Okay, so I'll just draw it right here for reference. Some of you guys look puzzled. So if I'm coming from the left, I'm diving down. Diving down here is negative infinity. Okay, it's going infinitely down. Okay, a question, Bobber? You have a question?
No, I was just realizing that wasn't my task.
Oh. As x gets closer and closer to our principle from the right, it shoots up to pos infinity. Okay, good. Any questions? Doing okay? You guys remember asymptotes a little bit? Okay, so asymptotes. A line that curve approaches more and more closely is called an asymptote, which, with reference to the exploration on the previous page, as x gets closer and closer to 1, the graph gets closer and closer to the equation x equals 1 but never touches it. Okay, so that's when our x's we plug in, we can do 1.01, 1.001, 1.001. It just gets closer and closer to it and rising, rising, rising. Okay, the graph of the infinite discontinuity at x equals 1 is called your vertical asymptote. Okay. This occurs at 1 because of 0 in the denominator, which we've talked about. Okay, and what this is saying is that this is the part I was telling you guys about the horizontal asymptote. That's the thing they kind of add. So in Math 20, we kind of skim over that horizontal asymptote. We don't really explain it. And now we're going to talk about it a little bit more. So it says as your x increases in value, so both plus or minus, so a bigger negative, a bigger positive, you'll see that it gets closer and closer to y equals 0, but never gets y equals 0. Again, this is what I've already said. Okay, so the line of y equals 0 is called our horizontal asymptote. So in this case, we have a vertical and a horizontal. But rational functions, okay, from Math 20, as long as the bottom's growing bigger than the top, you're going to have a horizontal asymptote at 0. Okay, it's always going to happen. Okay, vertical and horizontal asymptotes are often represented on graphs with dashed lines, but these dashed lines do not form part of the graph. So we use the dashed lines as our barrier just for reference, okay, but they're not part of the graph really, okay? So that's why I'm saying when you see it in your calculator, you're not going to see a dashed line or anything. All right. Okay, so investing asymptotes as a graphs here. So let's look at these. Okay, so consider the function 3 over x. State the domain of the function. So what's the domain of this function? What's that, Key? Right, so he's saying greater than or smaller than 0, but you also simply can write everything except 0. So you can say everything but 0, but he said this is also fine. Pretty much he's saying greater than 0 and less than 0. You could write it like that if you want. That just means not 0. Okay, it's not equal to. There's a lot of different ways you can write it. Okay, but the point is it's just everything but 0. Use a graphing calculator to function, but do not sketch on the grid. Okay, so we're not sketching on the grid yet. So if you want to use your graph calculator, you can. I'll go ahead and wait for you guys, let you guys do this once here. All right, so you sketch on your graph calculator, so that's good. So now we're going to look at write the equation of the vertical asymptote using the information from A and B. So obviously the vertical asymptote, we just can't be 0. So your vertical asymptote is going to be in the form of x equals 0. So if you do your dashed line here, it's just simply going to be the y-axis for this one, right? So we just did D, I just put on a dotted line. Now state the horizontal asymptote. Okay, well, this is what I talked about. Is the bottom growing faster than the top? Yes. The top is held at 3. The bottom's going to be 3 over a million, 3 over negative a million. So it's going to be really, really small numbers. So it still is going to be y equals 0. So it's the x-axis. Simply, your asymptotes for this one's kind of the easiest one. Your asymptotes are the x and y-axis in this case. So it'd be y equals 0 for that. Okay, complete the graph on the grid. So you can always just try a point to see where it's at, because really what happens with these is they're going to be symmetric in terms of the diagonally. So they're not going to be stacked ever, because that wouldn't be a function, right? And so you're going to try to keep them, they're going to kind of be like either here, here, or maybe here, here, kind of like diagonally. So to kind of figure out where they're at, you can just plug in a point. So for example, it's really easy on this one, because if I plug in a negative x, my answer is going to be what? negative. So I'm in the third quadrant. I put a negative x, I got a negative value. Okay? If I put in a positive, I'm going to get a positive value. Plus, plus. Right? So that's kind of a way you can just kind of figure out what you're doing. And then if you're asymptotes, this kind of seems a little bit, I don't want to say obvious, but when you're looking at this, the only way I can hug the asymptotes is drawing it like that. That's the only way it's going to work. Like if you try to draw it any other way, you're not going to hug your asymptotes appropriately. So that's kind of zeroed into what it's going to be. Okay? You can get actual points and make it more accurate, of course. Okay? But I'm just kind of generalizing that that's how it has to be with your asymptotes and knowing in which quadrant it's going to be. A few of you guys have asked me a few times. Remember, quadrant starts here. 1, 2, 3, 4 for future reference. Okay? You always start, what's an easy way to remember why that's 1? Why would that one be 1? Positive, positive. Yeah, that's the simplest section, right? Plus, plus. Okay? So start with the simplest, counterclockwise. Okay? All right. Yes, cast did go that way, exactly. Yeah. Except for cast started here, though. Because remember, this is all. Yep, and trig. We'll come with, yep. Unit circle cast stuff is important. Okay, state the range. So what's the range of that function then? Exactly. Y. Yep, y is everything but 0. Okay, perfect. All right, part 2. Let's look at another one. All right. Okay, so this one, we have the function of 2x over x plus 1. Now, this one's a little tricky because we'll investigate, but now I have a single x on top and a single x on bottom. So in my mind, those are growing similarly. Okay, they're growing similarly. They're not going to be as exactly, the bottom's not growing way faster than the top. So state the domain, though. So what's the domain? Yeah. X can't be negative 1. Is 0 okay? Yeah, 0 on top's fine. 0 on top's fine. Okay? Go ahead and use your graph calculator. Graph this real quick. I'll pause the video again. Okay, so everybody has that in, so you're kind of looking at it. Again, Keegan made a great point. He said, it's above the x-axis. Yep, that's something to observe. That's something we're going to pay attention to. Good. Okay, and he's talking about it. Last few have been on the x-axis. It moved this time. So it says, write the equation of the vertical asymptote. So let's go ahead and do that real quick. So how would you write it? It would be x equals negative 1, right? So x equals negative 1, so I have a vertical asymptote right here at negative 1. Show the vertical asymptote on the grid with a dashed line. Just did that. Now it says estimate the equation of the horizontal asymptote. Verify the equation by using the table feature. So go ahead and look and see, guys, what's happening for the horizontal asymptote. So what it's saying is look and see where's it flattening out at. It's getting really close to 2. Good. That is your horizontal asymptote. Who can see why? Number on top's a good observation, but not completely right, Dom. That's close. Okay, so here it is. This is actually, I'm going to give you a very simple version. Okay, so when the bottom's growing faster than the top, we realize that the horizontal asymptote is what? 0. Okay, that's the first one we did. This is a situation where they're growing equally. Why they're growing equally is because it's a 2x, that's a degree of 1, and a single x, degree of 1. What's the ratio of their leading coefficients? 2 to 1. That's how you get the horizontal asymptote when they're growing the same. I'll say it again. They're growing the same because they're a degree of 1 each. X to the 1, x to the 1. The leading coefficients are 2 and 1. 2 over 1 is your horizontal asymptote. Horizontal asymptote. Yep. For when they're the same degree. Okay? So we did that. So we did, it is y equals 2. Complete the graph. So now we're going to complete the graph. The graph looks like so. So that's what your graph looks like. So state the range of the function. The range is then, obviously, the range is y can't be what? 2. Good. Good. And we're going to look at the third option. So there's 3 options. Bottom growing faster, bottom and top growing equally, top growing faster. The next one you can see, the top is what? X squared. The bottom is an x. So we're looking at that situation where the top's growing faster. So let's just think about this just for a second, guys. Do we have horizontal asymptotes on x plus 3, the line? Let's just think about this. I'm going to kind of spoil the next thing. No, x plus 3. And let's just write x plus 3 as a rational function. What would I write it as? Over 1, right? If I didn't want to write it as a fraction. What's growing faster? Did we have horizontal asymptotes with x plus 3? No. So you won't have it when the top is growing faster. Okay? Wait, is that making sense? So, here we go. X squared over x minus 2. The top's growing faster. I kind of spoiled that part for you, but that's good. Draw the vertical asymptote on the grid. So the vertical asymptote is at 2. Okay. Use the graph calculator sketch. Go ahead and do that. I'm going to keep going here. And then this one, does it have a horizontal asymptote? When you graph on your calculator, you're going to see it does not, for the reason I explained. Okay, you have to pay attention to the degree. Okay, this is a 2, this is a 1. This is growing faster. GF, it's growing faster on top. So there's no horizontal asymptote. Okay, so the picture is going to yield a little interesting picture. It looks something like this. Like that. And then it's going to have a little mini one up here like that. Okay. So in terms of the domain still looks like it's what? What's the domain still look like it is? Right, it just can't be 2, right? Because it's approaching 2, and then it's growing away from 2. It's approaching 2 and growing away from 2. So it's still just simply the domain is x can't be 2. How about the range? A little bit tricky here. And this one says use your graph calculator to help find. How would you do that with your graph calculator? Let's see if you guys can answer this on your own. What would you intuitively do? Good job, Ty. Find the max here. Find the min here. Your range is this and lower, this and higher. So there's a gap that you can't have. Okay? You're going to be between those. To save some time here, you can do it in your calculator right now. I'll pause it, but I'll just let you know that you should get less than 0. So y should be less than 0. Y should be greater than or equal to 8 for all reals. All right, here we go. Last couple pages. So, pre-investigation, the horizontal asymptote falls into one of 3 categories. And like I said, I'm beating a dead drum here because I just said this like 3 times. Okay, so the graph horizontal asymptote is 0 in part 1 when the top is growing faster than the bottom. Or sorry, the bottom's growing faster than the top. Of course, I said it backwards the first time. Okay, when the bottom is bigger than the bottom, the bottom is bigger than the top, it's going to be 0. When they're equal in terms of their growth, it's going to be their ratio of their leading coefficients. The graph has no horizontal asymptote when the top is growing faster than the bottom. Okay, so we'll investigate how the degrees of the numerator and denominator affect the asymptotes. Okay, so the graph calculator has limitations when graphing some rational functions. The suggestions below may help clear that up for you. So the calculator is in connected mode, which most of you guys are in connected mode. A line will connect 2 parts of the graph. This line is an approximation of the vertical asymptote. If the calculator is in dot mode, neither the vertical asymptote or horizontal asymptote appear. And then using the zoom decimal, it can zoom in to see what your asymptote is in terms of where the gap is. Okay, so that can give you a clear representation of the graph. So maybe before next notes, we'll go over that. So get that set up on my computer one. Do which part? Just connected mode and dot mode? There is modes of part when you go to graphing settings.
And D-decimal or Z-decimal?
Z-decimal, so we're doing that just gives you the decimal window so that you can see things a little bit clearer in terms of the values. So it's more of just a tool. But, I mean, I think a lot of things that we just did, we kind of know. So, but we'll go over Zoom decimal for sure tomorrow. Okay, we'll do that. So you guys have to, well, we'll go over all three. That's fine. We'll do that tomorrow. We don't need it for right now. Okay, and algebraically determining the equations of asymptotes. So in part 1 and part 3 are examples of following rules which we use algebraically to find the vertical and horizontal asymptotes. These rules apply for all rational functions when they have factors have no factors in common. Today we're talking about when they have no factors in common. Tomorrow we're talking about when we have factors in common. So we'll get into that tomorrow. But that's the point of discontinuity because that's the vertical asymptote that breaks the graph. Okay, so it's just summarizing things we've already talked about. Okay, vertical asymptote, 0 from the bottom. Horizontal asymptote, relationship of the top and bottom. And let's look at this one. This is all we got, and we're done. Okay, so this says algebraically determine the equations of the asymptotes of the graph. There, verify using a graph calculator. So all it wants is the equation of the asymptotes. So we can do horizontal as the easy one. So I just look at it right now, and I say x squared and x squared. Okay, they are the same. So then how do I get the horizontal asymptote? 1/2, the ratio of their leading coefficients. 1/2. So your horizontal asymptote is y equals 1/2. Okay. Again, x squared, x squared. They have the same growth factor, the same degree. So you look at 1/2. 1/2 is where I'm getting that number. The ratio of those numbers. Any questions? See some confused faces. Questions? Okay, vertical asymptotes. I don't know what makes 0 on the bottom, so what do I have to do? Factor. We need to factor the bottom. So we do this is decomposition because there's a number in front. So 2 times -3 is -6. Factors of -6 that gave you -1 is -3 and 2. So you rewrite it now, 2x squared plus 2x minus 3x minus 3. And then we group. You can factor however you factor. This is how these AVP workbooks teach it. It's simply the AC method, which is widely used for factoring when the number is not 1. So now we pull a 2 out and an x. We get x plus 1. Pull a -3 out, x plus 1, and we have it factored. So the bottom is 2x minus 3, x plus 1. So my vertical asymptotes, I have 2. They are x equals -1 from here, and x equals 3/2 from here. Okay. All right. That's it for that.